In this example, we have a car traveling over a hill. In transportation, this is what we call a crest vertical curve, and this curve is represented by the function 0.2x minus 0.001x squared. Our initial velocity, when x is equal to 0, and when the car starts on the curve, is 37 feet per second, and it has a constant acceleration of 5 feet per second squared. We want to find the magnitude of the acceleration when it's traveled along the curve 150.75 feet, which corresponds to an x position of 150 feet. Well, we have a constant acceleration problem here, since we know that our tangential acceleration is 5 feet per second squared. However, nowhere in the problem is time mentioned. So the constant acceleration equation that we want to use is our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration, final position, minus our initial position. We want to find what our final velocity is so that we can find our normal acceleration. So our final velocity becomes the square root of 37, which is our initial velocity, squared, plus 2 times 5 feet per second squared, which is our initial acceleration, or our constant acceleration, times our final position minus our initial position. Our initial position is 0, and our final position is 150.75. So that difference is 150.75. Solving that, we get that our final velocity is 47.29 feet per second at the position of x equals 150 feet, or a distance along the curve of 150.75 feet. Next, we'll need to find our radius of curvature. Just a reminder that our normal acceleration is equal to the velocity squared over radius of curvature. So our radius of curvature equation, rho, is equal to 1 plus derivative of y with respect to x squared to the 3/2 divided by the second derivative of y with respect to x. Our function y is equal to 0.2x minus 0.001x squared. So our first derivative with respect to x will be 0.2 minus 0.002x, and our second derivative will be equal to negative 0.002. Plugging these values into our radius of curvature equation, we get our radius of curvature is equal to 1 plus the first derivative, which is 0.2 minus 0.002x squared to the 3/2 divided by 0.002. If we put in 150 for x, we get, which is equal to 507.52 feet. I'm not going to worry about this negative sign, because in my radius of curvature and my normal acceleration, it doesn't matter. My normal acceleration, we always assume to be positive and pointing towards the center of curvature. So I have my radius of curvature, and I have my final velocity, so I can then calculate my normal acceleration. Normal is velocity squared over radius of curvature, as we stated earlier. So we've got 47.29 squared divided by 507.52, which gives us a normal acceleration of 4.407 feet per second squared. I can then find the magnitude of the acceleration as being equal to the square root of the normal acceleration squared plus the tangential acceleration squared, which is equal to the square root of 4.407 squared plus 5 squared. That gives me a normal acceleration of 6.66 feet per second squared.